Hello, this is Maggie, and welcome to our third and final video of the Schaffer-Nishimura lab tour. In this video, we're going to start in the student offices and finish in the imaging lab where they keep the giant microscopes. We hope you enjoy.
Are you going to show any of the offices?
I don't know. Should I?
Waiting to see offices. Make all the people say hi.
This is our student office. It's vacant.
Hello, how's it going?
PhD students.
This is weird for us too, Rick.
Yeah, this is Chris and Azomi checking up to make sure their students are right.
Oh, that's why you wanted to come in. Okay.
This
Picture of that neon sign on the wall. That thing. So that represents a mouse with a laser for imaging.
Oh wow!
That's actually a gift from students. So that represents what we do.
Wow, that's pretty special. Look at that. Yeah.
All right, so what you see here is all the parts that we use for the microscope. So basically like objectives, mirrors, plates, all sorts of little things that we use to fabricate our microscopes because they're custom made. We don't buy them from a company. We make them ourselves.
Oh, wow. Good for you.
Yep.
All right.
Now we're gonna
Mike,
Who provides the parts?
our company. Our labs.
Okay.
I was going to say Mike might appreciate. I don't know if you were around when he was saying his background is engineering, right? Chemical engineering, but you probably have an appreciation for making your own parts if you don't have the right ones.
So we had a very good analytical lab as part of our group for a long time too.
And this is the laser room. So this is the laser room. We have 4 microscopes here, one on each corner. And here we have the spots that you see here. These are lasers. So these are very powerful lasers, 3-photon and 2-photon lasers. And this is basically the light source that we use for our microscopes. When you imagine a microscope, you imagine like the typical, tabletop microscope like this, but we don't have eyepieces for that. And we don't use like a typical light source. We use 50-second laser pulses for imaging, and that's how we get
Refresh my memory on what's the advantage of the 3 versus the 2-photon?
Yeah, that's a very good question. So 3-photon offers a better resolution. So it's you're going to get better images. You can also go deeper into the tissue. With 2-photon, we are limited only to 500, 600 microns into the mouse brain. But with 3-photon, we can go up to 1,000 microns, or even more than that. So we can look at structures that are very deep into the mouse brain, like the hippocampus or the white matter. And with 2-photon, we can only see the cortex of the brain.
So for this most recent data set, we're using 3-photon?
No, I think this recent data set is 2-photon.
Still 2?
Yeah.
Okay.
So Nancy, you said something interesting there because you mentioned the hippocampus, and that's a part of the brain that's implicated in memory function, right?
It's very important for Alzheimer's.
Yeah. So using the 3-photon microscopy, then we could potentially see the blood vessels that are feeding that part of the brain. Is that the goal?
That's the goal. We haven't been able to make it work here just now, but we are working on strategies to access the hippocampus because it's so deep that you need a lot of power to get it in there. It's technically very, very challenging. So we are working on getting to the hippocampus.
Yeah. Well, good job for working on that. Thanks.
Fingers crossed, we will get there.
So when you're imaging one of these mouse brains, the mouse actually has to be held really still, right?
Yeah, so the mouse is under anesthesia.
Yeah, okay. Oh, okay.
Yeah, it's asleep. This is the anesthesia chamber. So we use anesthesia here with isoflurane. And then we use a little like head mount we basically like fix the head so that the mouse, even though the mouse is asleep, it's still breathing. So the idea is to have the head very still in order for us to take very nice images without any motion.
Right.
Yeah. I think I have a stereotypes here, the thing that I use for the head. Thank you. No, this is a heat controller for control the temperature of the mouse, because since they are asleep, they can lose heat very easily. They're under anesthesia, so you need to control their temperature. So we have that in here. And then the mouse will go in here, this platform, and then the objective will go here, this way. We don't have an objective here right now, but it goes over here, and then the mouse will go. And this is where we will see this. What you see here is they're all very similar. Some of them have different types of lasers. So if you want to see different colors, you can use one of the microscopes. Or if you want to use 3 photons instead of 2 photons, you can use this one. So the cool thing about these lasers is that the wavelength is far red. So it's not able to see with your eye, but you can. So with this part, you can see the beam here.
Yes.
So it comes from here, and then it goes all the way to all these mirrors, and then it gets from here all the way into the microscope. So this is a microscope.
Oh, go ahead, Mike.
Really neat. No, it's very
yeah.
it's fascinating. Yeah.
So if you hold your hand in front of it, you cannot see the beam?
If I hold my hand in front of the beam?
Yeah.
Yeah, but it will burn you. So.
Oh, I got it. Okay, I thought maybe that's something special about the paper that revealed the beam that was otherwise invisible, or it's just for safety.
Yes.
Got it. Okay.
It's not recommended to go here.
I thought maybe it was like, in a different wavelength or something that we couldn't see otherwise.
So if you use a paper like this, you can also see it. So here's also the same anesthesia, the temperature control. Here I have an objective. This is the objective we use. So this basically goes here. And then the light from the laser will go with this objective into the mouse.
But now by the time the light gets to the mouse, it's gone through so many different filters and lenses and things that it doesn't harm the mouse in any way, right? It's just reading information.
Yeah, and then we open here this box. We have a whole detection system where we can detect different colors. For example, we can detect blue wavelengths, green wavelengths, and red wavelengths. So we can use different dyes. What you see in the images of cell fractures is basically a dye that labels the blood plasma. So you can see all the vessels. But you can also label neurons, you can label other types of cells, you can label whatever you want.
Can you quickly explain how laser scanning is used to build up an image? Because remember, Mike has looked at tens of thousands of these 3D image stacks. So, explaining how the raster scanning works and how that translates. Yeah,
so that beam that you just saw goes through the objective, right? Through here. But on the back, we have mirrors. So we have like mirrors in this position. You know, mirrors that are doing this, basically. And what they're doing is that they're directing the beam like this. So it's called laser scanning. You're just scanning the field of view. And then you go 1 micron down, you scan again, and 1 micron down, and you scan again. And that's how you get all the three-dimensional images.
So we really build these images up 1 point at a time. We measure 1 point, and the next point, and the next point, and the next point. It's just going very fast. We measure about 1 million points a second, but we're just scanning point to point. And then we scan one plane, step down, scan another plane, step down. And that's why the images you see when you slide forward and back on the slider, it goes up and down in the stack, but it also goes forward and backward in time, because those two things are coupled because of the way we acquire the data.
Right. So how long does it take to image a whole image stack?
Probably 5 minutes.
Okay.
Yeah. Depends on how fast you're scanning. We can scan at different rates, but usually it will take 5 minutes to take one scan of 300 microns.
Nancy, Nozomi and I were cringing when you started, because you were very, I 100% trust you, but you were handling the microscope objective very quickly.
I'm not going to drop it.
I know you're not going to drop it, but you were, the microscope objectives are about $10,000. So we just.
Wow. Yeah, don't have too much coffee, right? Before you handle
100% trust Nancy. It just looked very quick. Yeah.
Have one data set up like 300,000 image stacks in it.
Yeah, I think we
You
did.
guys are really keeping Nancy busy for that.
Yes.
5 minutes a stack.
Yeah. Oh, yeah.
It takes a long
Right.
time.
One 5-minute image stack gets broken up into lots of small image stacks that are outlining each capillary. So probably one stack that takes 5 minutes would probably have 200 or 300 vessel segments in it. And each one of those would be a little mini stack that gets analyzed.
Thanks for that clarification. That's a lot more efficient.
Yeah, yeah. Oh, you were thinking 5 minutes for each little vessel.
300,000 times 5 minutes. When does Nancy eat or sleep?
Well, we're still not sure if she does, but it's not for that reason.
Okay.
Thanks. Bye.
Mike, see you soon. Nancy, thank you.
And that concludes the Schaffer-Nishimura lab tour. If you're looking for more information on stall catchers and the other kinds of research we do here at the Human Computation Institute, check out the links in the description. Thank you so much for watching. Bye!